All right, what is up? Here we are. We are going to be going over GCC, making sure that we're good to compile, because you got to be able to compile to view the assembly, to do a little object dumping, to be able to run C files, to be able to look at C files. We're going to assume that we are working with C files exclusively at this point. I think ultimately we want to be able to do this with executables, but we can, because that's what the object dump does. So once we compile the C file to an executable, we will do the same thing with the executable to see the assembly. And usually we'll be working with executables that are fishy and funny. So let's get to it. Bang! Alright, so let's start with a super simple C file. We're going to go ahead and, include standard IO. You just got to do that. .h, it's a header file. And then you need the main. I forgot about that. You need the main, and we're going to have a function called func1, and we're going to return 0 so that we know everything is Gucci fresh. And then in the func1 file, this is complicated stuff right here, what we're about to do. In the function, we're going to go int b, we're going to initialize the variable, we're going to declare the variable, then we're going to initialize it with the value 10. Now, we use the letter B just to keep you confused. We could have started with F, but we didn't. And we're going to print F here, and we're going to go ahead, and this is a D for decimal, digit, maybe? Integer, really, I guess. Not integer, though. Digit, maybe. Something. It's something, number. D for number, I think, is what they want you to believe here. And then we're also going to return 0 here. I don't think we actually need to return 0 here, but we will anyway, just in case. And we're going to go ahead and save that. And that is going to be the C file that we are going to work with from here on out. We're going to go through the pre-processing, compilation, assembly, linking, and I'll explain those now. So by default, GCC is going to put you with the AT&T syntax. This is generally what you see, at least on the YouTube tutorials that I have religiously watched, with very minimal value added to my knowledge. That's where you'll see the movels, and there's some additional commands here. The Intel syntax does the destination before source, which is similar to the RISC V, so it's a little more familiar, and it uses the brackets to specify value at, which is nice. Unless it's an LAE command here, then it's a little bit, the load will actually be the address, not the address at, but still, it'll be the value, the actual number. So that's, anyway, we are going to be using the Intel syntax because that is what I am learning now, and it looks cleaner to me, honestly, so I like it. Less symbols. Other than that, pretty much the same thing. Just when you are compiling with GCC, you do want to, and I am going to include this MD file here. This has been generated by God+2, I believe is what we call them now. So you're going to want the -M32 flag, and that's just going to put you in the IA32. We'll go through it, and we will stick with the Intel syntax for now. All right, so a little housekeeping. First thing, we got rid of the implicit declaration, and then per convention we put the function before the main just to clean things up a little bit. And also, since we want to compile 32-bit style, we do want to sudo apt get install gcc multilib, and we are also going to want to use gdb at some point, maybe not in this video, so you might as well run sudo apt get install gdb, and that should be it. We are going to be using the fno flag, which does something. Okay, so it is fun to use the terminal and do things complicated, but this is just way better. It's godbolt.org. We have 3 separate compilers, and we can compare the results with different flags. The O3, we don't need that. That's just a compilation thing that makes things better, maybe, but we'll leave it in for now. And as you can see, the fno pi does something, but the fpi does more thing. So I'll leave it up to you to decide which is the way to go. More is better sometimes. The F pick also does a little bit more, so it looks like we get a little more going on. That's not always the case. We are going M32 here, so we get the D word pater. Yeah, so godbolt.org is probably what we're going to be using from here on out, just because it gives us more to look at, and there's colors, and it's instant. It's better. So the O3 flag is just optimizations. We don't need it. It's for runtime stuff. We don't need it. Took it out. Usually leave it in just out of habit. So I thought, I kind of didn't really know what it was. But as you can see, the F and O pi is not going to do anything for this simple stuff here. I think that's really, if we have pointers and things like that, you can see there's no difference. And the O3 is going to move some things around to make things run a little bit better. But with just the M32 flag, we are in the same spot. So let's go ahead and break this down, and then we'll do another example, and we'll go on from there to try and see how we can understand what's going on when we're looking at an executable that we do not know what it is. Alright, real quick, we actually need to understand the stack and registers. I did not understand. I still don't, but I have a graph, I have a chart, and I have numbers and a keyboard, and we're gonna get to it today. So let's take a quick break and actually get the fundamentals down real quick. Okay, registers. It's the smallest amount of data storage available to the CPU on the CPU itself. And in IA32, each register is 32 bits, 4 bytes. We can store one integer or one 32-bit virtual address. That address gets mapped through a page table to a 48-bit address. That doesn't even matter. We can store integers and memory addresses in a register. The memory address is an integer, and the integers are going to range from about -2 million to 2 million. We have 8 of these registers available to us. By convention, 4 of them are pointers, and the other 4 are generally used to store integers. So 4 for storing memory addresses, 4 for storing integers, and 2 of the ones that are for storing integers, well, 3 of them, or actually all of them. You can put whatever you want in the 4 that are for storing integers, really. The ESI, EDI, ESP, and EBP are specifically set aside for storing memory location, and those memory locations are pointed to the stack, and the stack is a block of memory like an array. So let's take a look at the stack real quick. So for the purposes of this, the stack is spot in memory, contiguous, that has memory for other functions, local variables, and how things should move around, flow control. It's a last in, first out data structure. So the last thing that's pushed on the stack is the first thing that's popped off the stack. The ESP points to the top of the stack, which ends up being the lowest memory location, and the EBP points to the bottom of the stack, which ends up being the highest memory location in this case. So let's just take a look at what it looks like, and then we'll go back to the code and we'll see how it all comes together, sort of. Stack is on memory. The registers hold values that sometimes point to locations on the stack in memory. All right, so let's take a look. We'll start in the main. Here's the prologue. The EBP is going to get set to a value that whatever that the operating system thinks is appropriate. It's going to be the 0 value if we're pretending the stack is horizontal. The ESP is then going to be matched to that, and then 16 decreased by 16. Then we're going to call function 1. We're going to go to function 1. Same thing's going to happen. It might be in a different spot though. Doesn't really matter though. We're going to just say it's 0, ESP, and then we're going to subtract 24. And then we're going to move the value 10 to the memory location that's EBP minus 12. So we have 2 registers, one at 0, one at -24, and we're going to take 0 minus 12, go to that spot in memory, put the value 10 in it. Then we're going to go 0 minus 16, go to that spot in memory, put the value 420 in. Then we're going to go 0 minus 20, go to that spot in memory, put the value 69 in it, 0 minus 24, go to that value in memory, put 710 in it, and you can see 12, 13, 14, 15, that's 4 bytes, 16's free, 16, 17, 18, 19, 4 bytes, 20 is free, 20, 21, 22, 23, 4 bytes, 24 is free, 24, 25, 26, 27, 4 byte, 28 is free. Then we're gonna take that ESP that's already at 24 and we're gonna go 8 more down. There are 1, 2, 3, 4 characters in the string. Each character is 1 byte, so we got 4 bytes here. I don't think there's a null terminating, and then I'm guessing the other 4 are for the memory location of the printf function. So we're gonna fill those up. We're gonna call the printf function, and the printf function is gonna do what it wants to do. We're gonna push the value, which is B, and that's what we want to print, which is at 0 minus 12 in memory, that spot in memory. We're going to push that to the top of the stack, so it's the first thing that gets popped off, because it was the last thing that was pushed. And it gets popped off in the print function, and that's what gets printed. Then we're at negative 32. We're going to add 16 back to it. There's going to be some empty space there, and that's kind of wasted. We probably want to, look into that. Doesn't matter. We're going to leave this function, come back here. Now we have to return 0. The return register, or the register that by convention stores the values that gets returned, is the EAX register. We're going to put 0 in it, and we're going to leave and return. And the value 0 is in the spot that has the that should have the value to be returned. And that's what we're looking at. Usually we're trying to go backwards though. So we'll only have this and we won't have this. When we're just looking at this, we can see, all right, 4 values have been defined or set in memory. Another value is on the top of the stack. So that value is something's gonna happen to that value. This is the only value that anything really happens to. The printf function's called. It's nice that we see that. Usually we won't see that, and it'll be something like this. This is probably more like what we would see. We won't really know what function is called, but some function gets called. Maybe we can go to it. And then things get restored, and we go back in the main and we see 0s returned. With that knowledge, we can kind of maybe write things out or type things out and try and piece things together. So that's the general idea of what this whole series is going to be about. A lot of times you have an executable. I know I often don't open executables because I have no idea what's going on. So hopefully with this knowledge, now when we're on GitHub and we're looking at some of these models, they're not always executables, but a lot of times these models there's a lot of stuff going on, and it's hard to know whether it's malicious, especially when we get like a PT file or something like that that's supposed to have weights in it. Those get run like code, so it's good to be able to just get a quick look and see inside and see if anything's funky. And hopefully as we go along, we'll look at some malicious stuff and we'll be able to see some patterns in malicious code and know that something's funny. Like if we don't want to ever print anything and we see one value get pushed and something like this, we might be able to say, oh, okay, that's something's getting printed. That's weird. And know that, hey, maybe we don't want to run that. Pass it to GPT, say, hey, take a look at this. GPT will say, okay, it'll tell us what it does and we'll know. But without this knowledge, I don't know. I can't pass the whole PT file to GPT. So this is going to be useful. Trust me, as we go along, hopefully we will gain more knowledge. So here's kind of an example. This is going to be in Python, but the same thing will apply. Fortunately, Python, a lot of the PT files are in Python, but sometimes the whole thing will be in an executable, and it ends up being an assembly. I don't have an example right now, unless I'm using the Onyx model, and I don't I do, but to load it's just quicker to use this. Okay, torch, import torch. We can go pt file equals torch.load, and I have a model called YOLO v8 n.pt, and then we can print pt file, and here you go. This is the pt file. It's Python code. It's straight up Python code. Python is based in C, so if we're doing something with CUDA, it'll end up being C-like. And then we can view the C in the same way that we were viewing the C earlier. And you can see here, in this case, it looks pretty good. It's just defining a model, sequential models, a bunch of them. It is a transformer, so there's all kinds of stuff. There's a convolutions in here. So these happen to just be this. This is probably the either the input or the output. Probably the input, since this is where we're starting. And then there's a bunch of other crap here. Right now, this looks pretty good, but we don't really know. You could put anything in here. I could put, steal all the data code in there. I don't know. So you want to be able to recognize patterns. We might not need assembly for the PT files, but there's a ton of file formats. There's a ton of different model types. There's the model weights, then there's the model architecture. And this is just for models. There's blockchain stuff. There's a lot of different stuff that you download and just hope that it's not a virus. And if you're downloading stuff that's free and maybe released or maybe leaked or something like that, a lot of times The only thing you can really do is wait for some brave soul to download it and hope that it isn't malicious. So if we do this and we learn some of this, we're gonna be in good shape. We're gonna be in really good shape. So that's what we're trying to do here. Make sense of these executables. Make sense of the stuff that we'd end up downloading, because we are downloading a lot of stuff if you're doing this kind of thing, and we're downloading it from like 4chan. 90% of the time. So it gets sketchy a lot of times. So yeah, that's basically it. All right, so that was a pretty lame ass code example, but I do need to keep this video reasonably short so I can edit it and post it. We will definitely do more code because there's a ton of code, and we'll try and do some, downloading of stuff in the code or running infinite loops. That's probably next. If I'm up for it tomorrow, tomorrow is one of those days where I'll probably be motivated to do another one. But I think tomorrow's a machine learning day, so we're probably gonna finish up MNIST, which is so lame, but we have to do it anyway. So we'll probably do a video on MNIST classifier, just model from scratch, not from scratch, model using TensorFlow, but the architect, whatever. So we'll do something else, but we'll do more code examples. This is the real stuff. This is good to know. Just to be able to use a computer. So there's computer science stuff, and then there's like navigating the computer, and this is the real stuff. This is like, what if you know computers, this is the stuff you need to know. So I don't really know computers, so I'm more interested in this, but the other things are more popular. So we'll see what happens. Definitely I'll run some examples. I have the that thing there, the online compiler, fire. But I hope this was useful. Again, comment, email me if you want to, but the comments are better. I guess maybe maybe people are embarrassed to comment for some reason, even though it's anonymous. But whatever. Appreciate if you can likes are fire. So please go ahead and subscribe, means a lot. Appreciate everybody. Hope you have a fantastic, what is it, Friday? Hope you have a fantastic Friday. And we just be out here. We just be out here being out here. You know what I'm saying, man? You know what I'm saying? Like, we just gonna be here, So I hope you're here with me. Feel me? So let's get it done, folks. Peace.